Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to continue to talk about LeChatelier's principle. This is part 2 of a 2-part series. So if you didn't see part 1, I do have the link in the description below. It might be worth your while to pause here, go back, take a look at part 1, and then we'll just continue on. So in part 1 of the video, I did talk about what LeChatelier's principle was, a bit of the background. And I did talk about 2 out of the 4 stresses. I talked about what happens if you change concentration, and I also talked about what happens if you change the temperature. Okay, in this video, I would like to talk about what happens if you adjust pressure and volume. Those 2 tend to go together, so we will talk about them together. So basically, LeChatelier's principle says, if you have an equilibrium and you make a change, okay, you change concentration, temperature, pressure, volume, any of those, the equilibrium is going to respond. Basically, it's going to attempt to undo what you've just done. Okay, so if you apply a stress to an equilibrium, the equilibrium will change to relieve the stress. So if you increase the concentration of, say, the sulfur, the equilibrium will attempt to decrease the concentration of sulfur. If you increase the temperature of the entire equilibrium, the equilibrium will react to try and decrease the temperature. Pressure and volume will be exactly the same. If you make the pressure much higher, the equilibrium will attempt to adjust to reduce the pressure. If you make the volume larger, the equilibrium is going to respond to attempt to reduce the volume. Okay, no matter what you do, the equilibrium will attempt to undo it. Okay, so the best way to do this is through a table. So now I've got pressure changes and volume changes in the same table because they are related. Okay, think of it this way. If you were to, let's say that you have a balloon. Okay, you went to a birthday party, you went somewhere, you got yourself a balloon. So you have this very nice balloon. Now that balloon has a certain amount of pressure, right? Somebody blew up the balloon. It has pressure contained in it. It also has a volume. Now, it's not quite spherical, but if you wanted to, you could probably calculate the volume of the balloon. Now, imagine if you take that balloon and you put your hands on it and you attempt to squeeze it so that way it takes up less volume. You would like the volume to be smaller. So you take your hands and you squeeze the balloon smaller. If you keep squeezing, eventually the balloon will pop. That's because as the volume gets smaller, the pressure gets larger, right? You're trying to compress all of this air into a much smaller space, and it's fighting back. So as you squeeze it smaller, the pressure gets higher until eventually the balloon can't hold it and the air pops out. Basically, the balloon pops. So for this problem here, really increasing the pressure is exactly the same as decreasing the volume. They are identical. If you are decreasing the pressure, that's the same as increasing the volume. Okay, think about it like a tire on your bicycle or a tire on a car. So you've got the tire, it's filled with air, and it has an extremely high pressure. Now, let's say that you get a leak. Okay, you're driving down the street and you run over a nail. So now your tire has a leak. So now the pressure is decreasing, right? Because the air is leaking out. As the air leaks out of your tire, it's increasing in volume, right? It used to be trapped inside of your tire, and now as it leaks out, the volume of the air is becoming larger, right? It's filling up a larger space. So as the pressure in your tire drops, the volume is increasing. Now, for me personally, I can't really visualize the pressure change. Okay, for me, it's much easier to see a container gets larger, volume goes up, or a container gets smaller, volume goes down. So even if the problem does talk about pressures, in my mind, I automatically switch it to volumes. So if the problem said that the pressure is increasing, I would automatically in my head think of it as decreasing the volume. Okay, because they are equivalent, right? Increasing pressure, decreasing the volume has the same result. Now in this table here, what I've got it set up as is increased pressure here in this column, decreased pressure in this column, And the rows are all about how many gas reactants you have versus gas products. Okay, this problem here is all about gases. When we were talking about changing concentration, it didn't really matter if you had a gas or an aqueous or what you had. When we were talking about increasing or decreasing temperature, again, didn't matter if you had solids, liquids, gases, aqueous, doesn't matter. But when we talk about changes in pressures and volumes, it really only affects gases, right? If you have a solid, right, let's just say it's our marker here, right? If I put a normal amount of pressure on it, I squeeze it as much as I can, I'm not really going to change its volume, right? So solids and liquids, they tend not to have any effect when the volume and the pressure change. Like they just don't change. So when you're talking volumes and pressures, this one here really is only for gases. Okay, it's only for the gases. So you're going to count up how many gas reactants you have, and you're going to count up how many gas products. If you have more gas reactants, okay, you counted up the reactant gases, you counted up the product gases. If you have more gas reactants, these will be what happens to your equilibrium, forwards or backwards. If you have more gas products, this will be what happens to your reactants and your products. Okay? So let's do a couple of examples just to get a feel for how we use our table. So for this first one here, let's say that we are going to increase the volume. Okay, that's the change I'd like to make. Okay, so increasing the volume is in this column right here. Now all I need to know, do I have mostly gas reactants or mostly gas products? So if we count, over here on the reactant side, I have 2 SO2 gases, right? There's 2 of them. Oxygens, I have 1. There's 1 oxygen. So total, I have 3. There's 2 SO2s and there's 1 O2. So I've got 3 gas particles on the reactant side. If I look at the product side, I've got 2 SO3 gases, so that's 2. And this is heat. Okay, heat is included because this would be an exothermic reaction, so it is producing heat, but heat is not a gas particle. So the heat is not counted here when I'm counting gases. So if you've got 3 things that are gases on the reactant side, 2 things that are gases on the product side, then you have mostly gas reactants. Okay, so more gas reactants, that would be here. And I am increasing the volume. So if you have more gas reactants than products, you're increasing the volume. Your whole thing is going to go backwards. Which means for a short amount of time, instead of it being in equilibrium, only the reverse reaction will happen. Now, if we wanted to, we could say that, right? We could say that the reverse reaction, RxN is the abbreviation for reaction, is favored. There we go. The reverse reaction is favored. Now, in the reverse reaction, you're taking products and turning them into reactants. So the amount of your product is going to drop, the amount of your reactant is going to go up. So basically, you're making more reactants. So I could also say that the reactants are favored. Okay, that's 3 different ways to say the same thing. I can draw a backwards arrow showing that the reaction is going to go backwards. I could say that the reverse reaction is favored, reverse reaction. Or I can say the reactants are favored because I'm making reactants, right? All of those say the same thing. Depending on what assignment you're working on or what class you're in, your teacher will have a favorite. And whichever one their favorite is, that's going to be your favorite too. Okay, so let's talk about the next one. Let's say for the next one, I am going to increase the pressure. Okay, so if we're going to increase the pressure, that would be this column here. And again, for gases, when you're talking pressures and volumes, it's all about counting the gas particles. How many gas reactants, how many gas products. So if we do the counting on this one, over here on the reactant side, I've got a calcium oxide solid. That's a solid. For pressures and volumes, solids don't count, so that doesn't count. So I've got a CO2 gas, that's a gas, and I've got one of them. Over here on the product side, I've got a calcium carbonate, which is a solid. For pressures and volumes, solids don't count, so that don't count. So that was my only product. If that's my only product, how many gases do I have on the product side? I have 0. Right? On the product side, do you have any gases being made? None. So this one here, you're going from 1 gas reactant to 0 gas products. You have mostly gas reactants and very few gas products. So if we look here, okay, we are increasing the pressure. That would be this column. And I have more gas reactants. So more gas reactants. So more gas reactants, increasing the pressure. I would cause the whole thing to go forwards. Now again, there's more than one way to say that, right? The arrow pointing forward shows that the reaction should go forwards, but you can use your words. You could say that the forward reaction is favored. There we go. Or if the reaction's going forwards, what are you making? I'm taking reactants and turning them into products. So I can say that the products are favored because I am making products. Right? You're taking reactants, turn them into products. You're going forwards. All right, let's take a look at the last one. Now, part of the reason why, personally, I love the pressure volume way more than concentration and temperature is because something cool can happen. If you look at the last one here, let's say that I would like to decrease the pressure. Okay, I'd like to take the pressure and I'd like to drop it. So, decreasing the pressure is here. And I have to count gas reactants versus gas products. So if you look here on the reactant side, I've got 1 chlorine gas, 1. I've got 1 fluorine gas, that's 1, so I got a total of 2. Over here on the product side, I've got 2 CLFs. CLF is a gas, and I've got 2 of them, so I have 2. So I've got 2 reactants that are gases and 2 products that are gases. Which one's more, 2 or 2? The answer, of course, is neither one of them, right? They're both the same. This only works if you have more gas reactants or if you have more gas products. If you have the exact same amount, then the answer is going to be no change. Right? If you look at part 1 of the video series, the one that was talking about changes in temperature and concentration, they always have an effect. You add concentration, you remove concentration, something will happen. You add temperature, you remove temperature, something will happen. But for pressures and volumes, sometimes nothing happens. If you have the same amount of gases as reactants and the same amount of gases as products, nothing happens. There's no change, right? That's cool. That's a little bit different. So now, if you've decided that you're going to use the table, what you need to do is sit down and memorize it, right? This is something that you should be able to recreate from memory. So that way, if you're writing a quiz or a test or an assignment, you can just go to the side of your page and rewrite the table, and then you're able to use it. Now, the other way to do this is to think of it more like a party. Okay, so forget equilibriums for a minute. Let's say that you've decided that you're going to have a birthday party. Okay, you've invited some friends, you're going to have a birthday party. And you've decided that you're going to rent a room somewhere in town, right? There's somewhere in your town, your city, where you live, where birthday parties are held. And so you've decided to rent a room there. So let's say that you phoned them, you said, "Hi, I'm having a birthday party. I'm going to invite some people. I would like to rent a room." Okay. And so you're happy, you order your birthday cake, you order balloons, you got everything. The day before your party, the people that rented you the room phone. And they say, hi, sorry, we've got some bad news. The bad news is that the room that you booked is no longer available. So you're going to have to take this other room. We'll offer you a smaller room. Okay, so if I offer you a smaller room, okay, this is like a decrease in volume. Okay, so now let's talk about your friends. You had a regular sized room rented for your party. And so you had a guest list of maybe 10 people. When your party gets moved to a smaller room, there's not enough room for 10 people. So what you have to do is you have to invite less people. Okay, so here you had more people invited. Here you have less people. Now, for a second, let's drop the word people and let's call it gas. More gas and less gas. Well, now take a look. If we look at our table here, if I have more gas reactants and less gas products, okay, more gas reactants, and I have decreased the volume, it's a forward reaction, right? If I go from a big guest list to a small guest list, that works if the volume gets smaller because I have less room for people, right? So if I had more gas reactants, more people on my original list, and the volume decreased, the volume got smaller, then I really do need to go with less gas products, right? I prefer thinking about the volume one because I can literally think of it as, here's my original party room, and then I'm going to make a change to it. And if you're going to make the party room smaller, that's going to favor less guests, less gas. But if you made the party room bigger, okay, let's draw a little picture of that. Here's your original party room. They phone and say, hey, that original party room, not available anymore, but we're going to move you into the large party room. This is going to be an increase in volume. Well, you had a guest list of gases, people, and if you go into the bigger room, that means you can invite more people. So here you'd have less gas, and here you would have more gas, right? If you're going to increase the size of the party room, your guest list is going to go from a small guest list to a big guest list. So if we apply that to our problems here, okay? For this one here, I increased the volume. So picture it as I went from a small box containing this whole equilibrium, okay? So the reactants are in here, the products are in here, everything is in here. This is the original party. And then I've decided to make the box bigger. Well, by making the box bigger, I need more gases. I need more people to fill the space, right? If I've got a big party room, I need lots and lots of people to fill it. So I'm going to go from small area to big area. I need more things to fill it. So here's your two guest lists. That's guest list number 1. That's guest list number 2. Which guest list better fits a bigger space? The bigger guest list, right? 2 versus 3. 3 will fill this space much better than 2. So this whole thing will go in this direction. Because going this way, you take 2 gas particles and you turn them into 3. 2 gas particles would fit really nicely in the original space, but if you make the space bigger, 3 gas particles fit better. So it does go backwards, as we predicted. Right? So for this one here, if you're talking volumes, if you got a bigger volume, the arrow will always point to the side with more gases. If your volume got smaller, it'll always point to the side with less gases. Okay, so let's try this one here. So if I look at this, I am increasing the pressure. Now, increasing the pressure works great in a table, but it's really hard to think of increasing the pressure in terms of a party, right? How do you increase pressure at a party? So if it was me, I would automatically change this to the volume equivalent. So instead of pressure, I'm going to think of it as volume. And remember, they're opposite. If you're going to increase the pressure, you do that by decreasing the volume. So here's my original container. The whole thing was in this container. And I've decreased the volume, so it's gotten smaller. Ooh, that really is small. So if your party has moved from the regular sized room to the smaller one, okay, you went from a big room to a small room, you need to go from the big guest list to the small guest list, right? Because you're going from big area to small area. So you want to go from the side of the reaction with more to the side with less. So in this original party room, you had invited one person to be there with you. When the party room got smaller, what fits better, one person or no people? No people. So the arrow would point from the bigger number to the smaller, right? Your volume got smaller, so the number of particles should get smaller, which is what we had already predicted, right? So if you want to use the table, that's great, because you just memorize the table and basically you just read the answers off of it. But if you would prefer to think of it in terms of big volumes versus small volumes, more particles fill the bigger one, fewer particles fill the smaller one, if that works for you, then that might be an alternate way to do the problems. So once again, I'd like to thank you for joining me here at Chemistry with Dr. Clark.